find value in this video, can you please subscribe and give a thumbs up? Also, if you want to follow this science, you can go to our Patreon group. Right, the hidden science of cathodic protection inside and outside of the pipeline. This video is part of a series exploring real, measurable science in cathodic protection. Science that can be proven using your own instruments. What you're about to see challenges conventional thinking and introduces a method that allows measurements that were previously considered impossible. The development of the Alexander cell makes it possible to observe what would otherwise remain in the realm of theory, or what some might call quantum behaviour. The motivation for this work comes from real discussions between engineers. A question was raised: does the conductivity of the internal fluid inside a pipeline affect the external cathodic protection system? The traditional answer says no, that internal and external systems are separate, with no interaction between them. But this assumption does not stand up to fundamental science. To understand why, we must return to the basics. Electrical energy flows from higher potential to lower potential through all available conductive parts. This is not opinion. It is described by Kirchhoff's laws and Ohm's law. These laws do not apply selectively. They apply to the entire system. When we look at a pipeline, we must stop thinking of it as a separate parts. The metal, the coating, the external soil, and the internal fluid all form one complete electrical network. If the internal fluid is conductive, then it becomes part of that network. This means current can divide and flow through multiple paths, including inside the pipe. The misunderstanding often comes from the idea that there is no driving force inside the pipe because the anode is external. However, this is an oversimplification. The corrosion reaction itself releases electrical charge into the fluid, and these charges will distribute according to resistant paths. Even without a visible anode inside the pipe, the internal electrolyte can still carry part of the current. To make this clearer, imagine a coated pipeline with two defects. One defect behaves as an anode, the other as a cathode. The corrosion current flows between them. While most of that current travels through the metal, if the internal fluid is conductive, part of that current can also pass through the fluid. This is simply Kirchhoff's law of parallel resistances in action. When cathodic protection is applied, we introduce an additional current into the system. This current does not follow a single path. It distributes itself across all available conductive routes. This includes external and, where possible, the internal fluid. The system reaches an equilibrium based on these pathways. This is where measurement becomes critical, and where most existing methods fall short. In practice, we cannot measure absolute potential. We can only measure potential difference, voltage. Every measurement depends on a reference point. Without a stable and true reference, the data can become misleading. This is the problem that led to the invention of the Alexander cell. The Alexander cell provides a stable reference that allows us to directly observe the corrosion reaction and eliminate distortions such as the IR drop. With this tool, we can measure what is actually happening in the system rather than relying on assumptions or indirect interpretations. Using this approach, we can identify how internal conductivity influences external cathodic protection, quantify its effects, and understand the true behaviour of the system as a whole. This is not a theory for theory's sake. It is a practical, testable science. You can verify it yourself using basic instruments such as a multimeter. The key is understanding what you are measuring and why. In one real discussion, a reader initially argued that the internal conductivity had no role, but by applying first principles, drawing the correct circuit and following the data, it became clear that the system behaves differently than expected. The conclusion was not based on opinion. It was based on the laws of physics, and that is the point of this work. We are not presenting ideology, we are not asking for belief, we are presenting science that can be tested, measured and proven. In a world of conflicting claims and assumptions, this approach matters more than ever. This video is only the beginning. In the next parts of this series, we will go deeper into internal corrosion, complex systems with sacrificial anodes, and real measurements using the Alexander cell. The goal is simple: to replace assumption with understanding and follow the data where it leads. As one reader concluded after exploring this approach, "I am so happy to know you. I try to learn more." This is where real science begins. If you like this video, give it a thumbs up, a like, and also subscribe. Also, if you want to follow this science more deeply with responses from scientists and experts, then join Patreon group. Okay? Thank you for listening. Bye-bye.